A cantilever beam of diameter d, that is the circular in cross section, and the length equal to 100 mm is subjected to force P equal to 5 kilonewton. So this force is same as equal to P is equal to 5 kilonewton. The maximum normal stress you have to induce in the beam you have to find out. Now clearly here the eccentricity of this force from the centroid at a distance equal to d by 2. So we have eccentricity will be equal to d by 2. For analysis purpose, we'll cut here at a particular section, distance equal to x, and we can develop the FBD. This force is the external force, so we have to show here the internal reaction. Internal reaction will be exactly opposite. That will be equal to same as equal to 5 kilonewton. So this one is same force equal to F will act, and it will develop a stress. That stress will be same as equal to the tensile stress, and that stress is uniform over the entire cross section. And this force F about point B will make a clockwise moment. You have to show here one internal reaction, and we have to show this internal reaction in an anti-clockwise signs, so that external clockwise will be get cancelled, and we have value of M is same as equal to the force F multiplied by E. This time the value of force is same as equal to 5000, and we have eccentricity equal to d by 2, that equal to 20 divided by 2, which one equal to 10. So we have moment equal to 50,000, that will be Newton mm. Bending moment here will develop the positive as well as negative stress on the top and bottom fiber. The maximum normal stress we are interested. Since this one is a tensile stress, so this stress will be positive value, and again for bending moment you have to take the positive value. So to find out the maximum normal stress, so we have sigma maximum normal stress means along the x direction. So sigma maximum normal stress is possible when we'll take the axial stress, which is tensile, plus we'll take the bending stress is also tensile, but we'll select here the maximum value of bending stress. Sigma axial is same as P divided by area. Bending stress will be equal to M multiplied by C divided by I. Here the value of C for circular section is same as equal to diameter divided by 2. So for circular sections, maximum value of the top fiber or bottom fiber from the neutral axis is d by 2. And value of M is known, the value of P is known. So we can solve this equation. We have P is same as equal to 5000, that will be Newton, divided by area. Area is pi by 4 into d square, so 4 will be shifted in numerator. We have diameter equal to 20 square, so we have 20 square plus bending moment M is equal to 50,000, so we have 50,000. Eccentricity equal to d by 2. D by 2 is same as equal to 20 divided by 2 divided by moment of inertia of a circular section, which is equal to pi divided by 64 will shift in numerator, and divided by d to the power 4 is 20 to the power 4. Solve this, you will get a maximum value of bending stress. So this maximum value of bending stress is come out to be 79.6, that will be megapascal. A solid shaft is loaded as shown in the figure. We have given here two pointed load. One force is 12 kilonewton, let labeled as F1, which is acting at distance equal to 0.3 from the centroid, which is located at point B. And the second force is equal to F2, which is equal to 15 kilonewton. Let's say this distance equal to D1 and this distance equal to D2. Total diameter is given as equal to 1 meter, and we want to find out here the maximum tensile stress produced. So let's cut this bar here and we'll show the internal reaction. So in this figure we have two external forces are acting, one is F1 and F2. We have to show here internal reaction. These two forces are acting to the right, so we have internal reaction will be same as equal to F, and we'll assume the direction of F is leftward. We can find out the value of F from the equilibrium condition. In addition to that, the force F1 about the, let's say this point equal to point P, and we'll make a clockwise moment, and this force about point P will make a anti-clockwise moment. So one moment is a clockwise is 12 multiplied by zero point 0.3 is 3.6, and second moment is anti-clockwise is 15 multiplied by zero point 0.3, that equal to 4.5, means anti-clockwise is more. So in this case we'll assume the moment at this point. Since the anti-clockwise is more, we have to show the moment at this point is a clockwise moment. So let's represent here. We have a internal moment reaction equal to m. To find out the value of f here, we apply the equation of equilibrium. First equation we'll apply the summation of fx, and the rightward force we'll take as a positive value. This total sum must equal to 0. In that case, the value of f1 and f2 is positive. So we have f1 plus f2, and the value of f is negative. So we have minus of f equal to 0. In this case, we have force F is equal to F1, which is equal to 12 plus F2, that equal to 15. So total internal force will be equal to 27 kilonewton. Next, to find out the reaction moment M, we'll take the sum of moment of all forces above the point P, and we'll take the clockwise moment as a positive value. So the force F1 with a distance d1 will make a clockwise moment about P, and this sum is equal to 0. F1 multiplied by d1 is a positive value. F2 multiplied by d2 is a negative value. So we have minus F2 d2. And we have assumed here the m is positive value. So you have to take the positive sign for m. It must be equal to 0. So we get m is equal to F2 into d2 minus F1 into d1. Out of that, we have d1 and d2 is same as 0.3. F2 is equal to 15. So we have 15 minus 12. And d1 and d2 is 0.3. So this answer will be equal to 3 multiplied by 0.3, that equal to 0.9 kilo Newton meter. So moment M will produce here the bending stress, and the bending stress will be same as equal to M multiplied by C divided by I, and the value of C is same as D by 2, I value is same as pi by 64, D to the power 4. This value is positive and negative both, so you have to take the positive value, because this force will produce the normal stress axial, so that will be equal to F divided by A, and we have A is equal to pi by 4 D square. So in this case, the maximum normal stress will be sigma is same as equal to sigma axial, and we'll select the positive value of a bending stress. So you have to select the sigma b max. Here sigma is same as force upon area plus sigma b maximum is same as equal to m into c divided by I. The total force is come out to be 27 kilonewton, is 27,000 Newton divided by pi by 4. So we have pi, and 4 is shifted in numerator. We have diameter equal to 1. So we have 1000 square. Plus bending moment M is come out to be 0.9 kilonewton meter, is 0.9 into 10 to the power 6. That will be Newton mm, multiplied by C. C is D by 2, and we have D is equal to 1000. So we have 1000 divided by 2, and whole thing is divided by the moment of inertia is pi by 64. So we have pi, and 64 will shift in numerator. We have diameter equal to 1000 mm, and we have to take the fourth power of it. Approximately this answer is close to 43.5 into 10 to the power minus 3. That will be megapascal. But we want here kilopascal, so you have to multiply by 1000. In that case, our answer is 43.5 will be kilopascal. An eccentric axial force P, which one equal to 60 kilonewton, act at point D. So this one is point equal to D point, which must be located 25 mm below the top surface of the steel bar as shown in figure. Determine the depth D of the bar for which the tensile stress at A is maximum. He only says the maximum value is not given. It means that you have to use the mathematics concept here, that for a maxima, for stress is maximum will differentiate stress with respect to the variable and equate to 0. So there is a stationary point you have to find out. And once you find out the stationary point, then you have to find out what is the corresponding stress at point A. So we'll just enlarge this cross section here, and we'll show the point here D, which is 25 mm below the top surface. So this point is same as equal to the point D here, through which the force P is acting, and the magnitude of the force P is equal to 60 kilonewton. So from top, the point D is lying at 25 mm. The vertical depth D you have to find out, and the base is same as equal to the 40 mm. So we have B is equal to 40 mm. First we locate the centroid here, the centroid at point G here, and the distance of the centroid from the top fiber will be D by 2. So from the top fiber, the distance will be equal to D by 2, as well as for bottom is also D by 2. So the maximum stress will be at top fiber. That is, the point A is the top fiber here, and the point B is the bottom fiber. For both point A and B, the value of C is same, and that is equal to D by 2. But we don't know the D by 2. So if I locate the point G here, I have to locate first centroid. So this one is the centroid here, that equal to G. Then this distance is same as eccentricity. This distance eccentricity is same as this distance, which one is eccentricity. So in this case, we have eccentricity will be the top distance is D by 2. So we have D by 2 minus top fiber A to point D, the distance is 25. So we have E is equal to D by 2 minus 25 mm. Area of the given cross section is width B multiplied by depth D. Moment of inertia I is same as BD cube divided by 12. Distance C already we have done. So we have distance C is equal to D by 2. That will give the maximum stress at point A and point B. One will be tension and one will be compression. Now to find the effect of the force P on A and B, we have to shift the force to the centroid, or you have to cut the section. Anyone you can do. So this time I will shift the force to the point G. If the force is shifted, then the force will remain same, and it is still directed outward, that equal to the force is equal to P, and this force P is equal to same as 60 kilonewton. And this force about point G will make a clockwise moment, and that moment will be like this. So this one is a case of hogging. So in this case, we have value of M should be taken as negative value is minus of P multiplied by eccentricity E, and we have eccentricity E is equal to D by 2 minus 25. The force P will develop the tensile stress at point A, and the M, the bending stress, we can calculate using the flexure formula at point A. For point A, we have the distance YA, you have to take the positive distance. So in this case, we have YA will be same as equal to D by 2 and should be taken as positive distance. So for point A, we have axial stress is tensile in nature. Tensile in nature is positive. We have P divided by area A. This time we have area is B into D. So we'll keep P as it is divided by B divided by D. Values we'll put later on. And the bending stress is minus M into Y divided by the moment of inertia equal to I. The moment is negative this time, so we have minus and minus become plus. So we have M is replaced as minus of P. This minus will become positive. We have P multiplied by E multiplied by Y divided by I. And we have eccentricity is same as D by 2 minus 25. So we have P multiplied by E. E is equal to D by 2 minus 25. Value of Y is YA, that equal to D by 2. So we have D and divided by 2. So 2 will shift in numerator. Moment of inertia is BD cube by 12. So we have multiplied by B multiplied by D cube, and 12 will shift in numerator. So we have 12 here in numerator. This time the 2 and 12, so 6 is left in the numerator. So finally we are getting here the bending stress at point A is equal to positive value is 6 times of P multiplied by d by 2 minus 25 divided by bd cube. bd cube. Here d is present in numerator, we have d cube, so it will become here that this term is cancelled and we left here with d square. So we have bending stress at point A is same as equal to P multiplied by 6. So we have 6 times of P multiplied by d by 2 minus 25 is divided by bd square, b into d square. Now we can calculate here total stress. Total stress is same as the axial stress given by equation 1 plus we have bending stress given by equation 2. So in this case the total stress will represent as sigma is same as equal to P divided by B multiplied by D plus we'll expand this bracket here. 6 and 2 become 3, so we have 3 times of P. In denominator we have d square and numerator we have d, so one term of bd is left. Then we have minus 6 into 25 is 150 times of p divided by bd square. So in this case this is 3 times of p by bd and this is p by bd, so we have stress is equal to 4 times of p divided by b divided by d minus 150 multiplied by p divided by bd square. So clearly here the width b is constant, p is constant, and the sigma is a function of the depth d. So this time sigma is a function of the depth d. So what we'll do, we'll differentiate sigma with respect to the depth and will equate to 0. So if you take a derivative of sigma with respect to d, then 4p by b is common term. So we have 4p divided by b. Derivative of 1 by d is minus of 1 by d square minus of 150 into p divided by b is a constant term. Derivative of 1 by d square is minus 2 divided by d cube and is equal to 0. What we observed here is that the b term will be get cancelled because on the right hand side we have 0 and the b is non-zero term. In addition to this, the p is also get cancelled because it's a non-zero term. We have minus 4 divided by d square and minus become plus. We have 300 divided by d cube, that must equal to 0. So this time d square and d cube, so 1 d is left. So we have minus 4 times of d plus 300 is equal to 0. And if you solve this, you will get this value of d, that is for maximum stress at point A, the required depth is 300 by 4, that equal to 75 mm. Once we put the value of d in this equation, that is equation number 3, we can able to find out the maximum stress, that is the total stress at point A. So from equation 3, the total stress at point A is 4 times of P, is 4 times, we have P is equal to 60 kilonewton. 60 kilonewton is 60 into 10 to the power 3 divided by B multiplied by D. B is equal to 40 and we have depth is equal to 75 minus 150 times P and we have P is equal to 60 10 to the power 3, that is Newton, divided by BD square. We have B is same as equal to 40 and D is equal to 75 square. Solve this, you will get the total stress at point A. So first term answer is 80, second term answer is 40. So we have maximum stress at A will be equal to 40 megapascal. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.